I'm going to go ahead and get started on this. I'm going to do this with a fake picture. Okay. And so the first thing is, if I need to break this into 3 rectangles, then I know that the total width of my region here goes from 4 to 10. So the width of each of my rectangles is going to be that total distance of 6 split into 3 pieces. So that means the width of each of my rectangles is 2. So if I'm thinking about like how this is broken up, we're going from 4 to 10. We're breaking it up by 2s. So that would look like 6, 8, 10. So those are my 3 pieces. Now, if we were doing left endpoints, then I would be using 4, 6, and 8 as the X values to get my heights. If I was doing right endpoints, I would use 6, 8, and 10. But this actually told me to use midpoints. So now I have to find the middle of each region. And I've been nice. I've made all of the middles whole numbers. If they're not whole numbers and they're fractions, that's okay too. We can handle fractions, but I gave us nice numbers this morning. So the middle of 4 and 6 is 5. The middle of 6 and 8 is 7. And the middle of 8 and 10 is 9. So that means that when I'm going to look for the area, I can put that width of my rectangles out in front. And then I'll be looking for f of 5 plus f of 7 plus f of 9 in terms of picking up those heights. I didn't give us a function, so to get those values, we're just going to use what's in the table. So f of 5 is negative 0.4. F of 7 was 1. And f of 9 was 2. So I'm looking at negative 3.4. And then I'm multiplying that by 2. I think I get negative 6.8. Is that what other people got? Before I move on, questions about this one? Yeah. Yep. Was that your question also?
Yeah. Yeah.
Oh, or I added it wrong. Oh, yeah. See, I was kind of waiting for someone to call me out on that. So negative 6.8 is not what you got? What's 1 plus 2? And I'm adding negative 0.4, so I should actually be at, and 2.6 times 2 is really how many people got 5.2? Cool. So, 2 things. One, it's always better to call me out if I make arithmetic in the moment. So then everybody has something correct in their notes. So for sure, call me out in the moment if you think I've made a mistake. Next piece of that. How many people would like another practice problem to try? I'm gonna do this one with a picture. Because we know what this graph looks like. So e to the x kind of does this. And we're looking from 1 to 5. And we're breaking that up into 4 rectangles. So I know that the width of each of my rectangles, the total width of the interval is 5 minus 1 or 4. And then I'm breaking that up into 4 rectangles. So each rectangle has a width of 1. Since we're going to use right-hand endpoints, 2, 3, 4, that means that I'm going to use the 4 values of the function, the 4 right values. So 2, 3, 4, and 5. So I know that my total area here is looking like that width of 1 times f of 2 plus f of 3 plus f of 4 plus f of 5. If I were to draw those in, for that first interval from 1 to 2, I would be using that right-hand endpoint to draw my rectangle. And from 2 to 3, I'd use the right-hand endpoint, and from 4 to 3, right-hand endpoint, right-hand endpoint. So when I'm done, I'm going to have an overestimate of the true area. In terms of putting this in, again, if I don't get a calculator, I'm really just going to be plugging these x values in. So if I plug in 2, I'd have e squared plus e cubed plus e to the 4th plus e to the 5th. By the way, if I'm adding those together, is there anything I can do to simplify? So if I was multiplying them all together, I could add the exponents. But unfortunately, if I'm adding them all together, I can't do anything. You could choose to factor out an e squared, but there really isn't a reason to do that. So I would walk away and leave the answer just like this. By the way, had a couple of requests to talk about that max-min theorem that came up on Friday. So let's kind of think about that in the context of this question. This is a nice, easy one to visualize, or a nice, straightforward one to visualize. So here's my e to the x graph. We know we're looking on 1 to 5. And the only thing that the max-min theorem is telling us is that if I wanted a not very good estimate for what the value of that integral is, I could use one rectangle. And if I use one rectangle, I know that if I choose the absolute highest point on that interval, which in this case would happen when x is 5, and if I just drew in one big rectangle at x equals 5, for sure the true area we're looking for is less than that. And that one big rectangle has a width of 4 and a height of e to the 5. Again, if I didn't care about a particularly accurate estimate, I could then say, well, I know the integral I'm looking for sure is bigger than me using one rectangle and picking the lowest height on the function. So if I pick the lowest height of the function from 1 to 5, that's going to happen at 1. And if I were to draw in this little baby rectangle down here, that thing, again, has a width of 4 and a height that we would get by plugging in 1 to the function. And that's really all that max-min theorem says. It's basically us saying, if we were really lazy, if we were not caring very much about accuracy, we were just trying to really get a rough estimate, we could just use one rectangle to estimate it. Dun, dun, dun. Can I flip the page? Got a couple people nodding heads to keep it up for a second, so I'll keep it up for a second. Okay, so places that we can go today, or places I plan to go today. I think that we should talk about definite integral notation and some of the properties. And then I think we've got time to talk a little bit about antiderivatives. On Thursday, we'll get back around to the fundamental theorem of calculus, which is going to tie these two things together. Or I can get ahead of lecture. But my thought was to not get ahead of lecture this week. If that sounds good to folks. Okay, so let's talk a little bit about definite integral notation. Which I've kind of been using, but haven't really talked about explicitly. So if I have some generic function that I'm going to call y equals f of x. So last week we did some Riemann sums and we looked at breaking up an area from A to B under the curve into a bunch of little rectangles. And then we said, let's let that number of rectangles go to infinity. And if we do that, we're going to get the true actual area. And we had that crazy Riemann sum notation. We did a whole bunch of algebra. We took a limit. We got to a final answer. Good news is we're not going to do very much of that this quarter. But we are going to do a lot with definite integrals. And so the way that this notation works is if I think about putting in one generic rectangle. So I'm trying to look at that area from A to B, and I'm going to put in one generic rectangle here. Well, the width of my rectangle, we've been calling delta x, but we can do that calculus thing that we did a lot in 17a and call that delta x instead a dx. And then if I told you that this generic rectangle was at some generic x value, how do we find the height of the rectangle? Let me rephrase that. If I told you that that rectangle was at x equals 3, how would you find the height of the rectangle? Where would I plug the 3 in? Totally. So I know that if this is at some generic x value, then I would get the height of the rectangle by plugging it into the function. So the area of this rectangle, if I think about it as just a height times a base, my base is that little bit of dx because that's the width of my rectangle. I would get the height by plugging it into the function. And then if I want the total area of all of the little rectangles, I need to add them up. And an addition problem is also called a sum. And summation starts with S. And that is literally why we put this stretched out S thing out in front. It means we're adding up that infinite number of little rectangles. Now, the other piece to this notation is we still have to know how far to the left did we take the rectangles, how far to the right did we take them. So we put an A down here and a B up here, which tells me kind of where to start on the left-hand side. And where to end on the right-hand side. And that notation is just a little bit cleaner for us, easier to work with as we move through more complicated problems. So for example, if I wrote something like -1 to 3 absolute value of x minus 2 dx. This notation tells me we're looking for the area. I need a graph of absolute value of x minus 2. So that graph is going to look like this. And that we're looking for the area that spans on the left-hand side all the way to -1. And on the right-hand side, all the way to 3. Now I've chosen an absolute value graph for a reason here. Because although we often read this as the area under the curve, I'm going to make the argument that that is secretly not the area under the curve. Because if I wanted the actual area under the curve, this area would keep going down forever somewhere, because that would be the actual area under the curve. So when we talk about it, we secretly mean it's the area under the curve, but above the x-axis. The reason that that's important in terms of notation is that we call all of these heights that are above the x-axis positive. And we call heights that are below the x-axis negative, because they have negative y values. So one of those properties that we have of this sort of notation is if I had something that maybe looked like 1 minus x squared dx, and I was talking about the area from 0 to 4. In terms of the picture that goes with this, I'd have this parabola that's concave down. And I would be looking for the area from 0 all the way out here to 4. Okay, my picture. Okay. We'll just use the whole sheet. My parabola, it keeps going down. We define this part of the curve to have negative heights. So when we think about this area piece, this part is going to have negative area. And this part up here above the axis, we would have positive area. So we define it above the axis as positive and below the axis as negative. The other way that this notation for definite integrals can switch from positive to negative is if I go backwards. And by go backwards, I mean, normally we're thinking about our x values moving towards larger and larger x values. But if I write my integral to go backwards, meaning if I, looking back at that first example, if I were to instead write this as 3 to -1 of the absolute value of x minus 2 dx, this is equivalent to the negative of the integral from -1 to 3 of the absolute value of x minus 2 dx. And really the only good reason that I can give for that, physicists invented calculus. That's all I've got. So physicists invented calculus, and this is all really connected to thinking about velocities and time and distance and things. And so when we have a negative velocity, we talk about a negative displacement or a negative distance because we're going in the opposite direction we were expecting to. And so one of those properties of definite integrals is that if we're going in the opposite direction we're expecting to, meaning the bigger x value is on the bottom, it's the negative of flipping those. Good times. Okay. One of the nice things about this notation is for functions that are nice to graph, it means that we don't have to estimate with rectangles. We can use our geometry skills. So let's do a couple of these where we use our geometry skills to find the answer instead of our rectangle estimation skills. I'll give us a simplified absolute value graph. But we're just going to evaluate the integral by interpreting it as signed area. That means we have to draw a picture. I don't have a way around that. If we're going to interpret this as signed area, we got to get a picture going. And my picture here for absolute value looks like this. And I'm going to go from -1 to +3. So the area that we're looking for is the area of these two triangles. And I will give you, I don't know, 2 minutes to find the area of those triangles on your paper. Start on this one. This small triangle has a base of 1. What's the height? So I know the area of this triangle is 1/2 base times height. This triangle over here, how wide's the base? And my height, because of the function, is also 3. So I'm looking at 1/2 the base times the height. So I've got 1/2 plus 9/2. Conveniently, they have a common denominator already that is 10/2 or 5. So that's what I get for a total area. Let me give us another common one that shows up. Let's go 0 to 4. The square root of 16 minus x squared. If you have taken calculus in a previous life and done some of these antiderivatives or integrals, this is probably still not something that you're going to do without a picture. I promise not to make you talk, but stick your hand up if you know what this graph looks like. Some people wish they knew what that graph looked like. Yeah, okay. So if I write this as y equals the square root of 16 minus x squared, I'm going to go ahead and square both sides. That's y squared is equal to 16 minus x squared. And if I were to add x squared to both sides, some people recognize it now. What's the radius of that circle? I heard a whisper. Say it with confidence. Yeah, the radius is 4. Okay, so this is a circle with a radius of 4, but you know how when we take the square root of both sides, we end up having to do that plus or minus thing? We didn't have the minus side. We only had the positive square root, which means this is the top half of a circle with a radius of 4. And the area that we're looking for is the portion from x equals 0 to x equals 4. So we're looking for this piece. What fraction of a circle is that? So if it's a quarter of a circle, then that area is going to look like 1/4 of the area of a circle. And the area of a circle is pi r squared. And our radius here is 4. Does anyone want more time? Not seeing any takers on more time, so let's go ahead and get this sketched out. So sine of x starts at 0, 0. Kind of does this. By the way, what's the period of just a plain old sine of x? Where does it end? Okay, that's kind of a trick question. It doesn't really end. Technically, it keeps going in both directions, but which means pi is in the middle. So pi over 2 is up there at that high spot, and 3 pi over 2 is down there at that low spot. So this corresponds to that area. And because we are talking about the signed area, this part up here is positive, and this part down here is negative. And because sine of x is beautifully symmetric, that positive part and that negative part cancel out, and this is in fact equal to 0. We don't have to know what the area in there is. It's enough to know that based on the limits I gave us, that area is going to end up being 0 because these two pieces will be identically shaped, but one is below the axis, one is above the axis.